All right, okay, so now I'm going to tell you the solution. Well, first, of course, we have to change our regressor here because we want to use our polynomial regression model, which is based on linreg2. So that's the first change, linreg2, yes. And now, in the predict method, do you think we need to keep x or change that by something else? Well, of course, we can't keep x, because remember, x is only that matrix of single feature containing the position levels. Remember that when we use the linreg2 regressor, which is the linear regressor, it has to be applied to the transformed matrix of features x into this matrix of features at the different powers. You know, position level, then squared position level, and then the other powers. Here we only chose n equals 2 so far, so we only have the squared position levels. But that's exactly what you need to change here. You can't keep x because it is the single feature, so you need to input here that transformed matrix of features x containing the different powers of that single feature position level. And that's, of course, exactly this polyreg fit transform method applied to this matrix of single feature x. So I'm copying this, and that's exactly what we have to input inside this predict method. You understand? So that was the little thing not to forget, and now you're all good. You're ready to have a beautiful visualization of the polynomial regression results. Let's just replace this linear here by polynomial, and now 100% ready. Let's visualize the polynomial regression results. And there you go. Now we have indeed a way more adapted regression curve coming indeed much closer to the real results, you know, the real salaries. Indeed, if we compare to, I'm going to zoom out a bit so that we can see both of them at the same time. There we go. So if we compare these points where we had issues previously with the linear regression model, well, we can clearly see now that the issue is resolved, because indeed the predictions on this blue curve come way closer to the real salaries. And this is only with n equals 2. I'm going to show you then that with higher powers, you know, n equals 3 or 4, well, we will get even better results. And I'm going to actually show this to you right away. So now what we're going to do is, well, we're going to keep this, but we're going to remove this because we're going to retrain the polynomial regression model with a higher degree. Let's take, for example, you can try with 3, but we're going to directly try with 4. So there you go. I'm going to remove the output, retrain the polynomial regression model on the whole dataset with therefore this time a degree of 4, which means that the polynomial regression equation will be salary equals b0 plus b1 times position level plus b2 times position level square plus b3 times position level at the power of 3 plus b4 times position level at the power of 4. So that will be the new polynomial regression equation. And so therefore, let's retrain it. Let's build this new polynomial regression model by just running this cell again. All right, so now we have it. And now, very simply, we're going to visualize the new polynomial regression results by clicking this cell here. And as you can see now, the polynomial regression model is perfectly fitting this data set. So here we clearly have overfitting, but that's okay only in this situation because we want to have a perfect prediction of the salary between position level 6 and 7. Okay, and now one final thing, because I really want you to have the best results and best visualizations. Indeed, as you can see here, what happened is that only some straight lines were plotted between each consecutive points of the dataset, right? And therefore that makes this curve not as smooth as we would hope for. So I actually prepared another code, but which we won't code together because this is just for the sake of having a more beautiful curve. So we're going to get it from the original implementation. It is actually right here. You see visualizing the polynomial regression result for higher resolution and smoother curve. So I'm going to take all this code and then paste it in our copy of the implementation right here in a new code cell. And you will see that we will get indeed a much smoother and more beautiful curve, as you can see, right? And the trick to plot this curve, I'm going to explain this quickly, is just to, instead of taking, you know, the integers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, well, we increase the density of these points by taking not only these integers, but, you know, 1, 1.1, 1.2, 1.3, 1.4, up to, you know, 9.1, 9.2, 9.8, 9.9, 10. That's what this 0.1 means. That's what we call the step. All right, so you don't have to understand this. You can if you want, but this is something you will probably do only once in your life, because I remind that usually your datasets will have many features, and here I only took one feature in order to show you the results on a graph, because if we had many features, I couldn't show this to you because we would have way too many dimensions. So don't worry too much about this, okay? But just appreciate the result, right? We have a very well trained and therefore very well fitted but overfitted model for this dataset. But that's fine, because then indeed we will be able to get an amazing and accurate prediction to figure out if there is truth or bluff.